one. Let's go. All right, homeostasis comes from homo, meaning same, stasis, think static. We know that from static electricity means stillness, right? But homeostasis is the process by which we are returning to a state of normality or a state of balance, is what homeostasis means. We want to describe the importance and then look at hormones, how to achieve blood glucose levels. So I'm going to go through 3 examples, one of which is in the presentation. And the other 2 examples I'm going to talk about from a homeostasis point of view. Okay, its importance. Our body, one of the priorities for life is that life remains in narrow limits. Yeah? Unless you're a tardigrade and are absolutely insane, you can withstand temperatures up to 1,000 degrees and have radiation pumped at you at over 1,000 times the background level. So tardigrades are the pretty much indestructible species on the planet. Humans, however, we're not so great, right? We're pretty adaptable. We're one of the most adaptable species on the planet. The fact that we're able to survive in Antarctica, right, through the use of technology, clothing, etc. So that we've had behavioural adaptations, less so at physiological adaptation, but we've had behavioural adaptations that have allowed us to spread out and conquer the world. Yeah. So when we're talking about returning to this state of balance, is about maintaining those narrow limits. So when we think about body temperature is narrow. Your core, your internal body temperature remains somewhere between 36 and 38.5 degrees, roughly. Yeah. Above that, you have fever. And what's happening with fever is if you get a temperature well above 40 degrees, that becomes a problem because cells start to die. Cells start to degrade, and right, so you get cellular death above 42 degrees. You reduce your core body temperature to, say, under 35 degrees, you go into hypothermia, body systems start to shut down. Yeah. If you cool the body temperature to under 20 degrees, which is what they do in open heart surgery, is you actually stop the heart from beating. Yeah. We need to do that process, in a controlled manner in a hospital. Okay, at the end of our last session with relation to, we talked about homeostasis from an oxygen point of view. You increase your exercise, your muscle intake of oxygen and burning of glucose increases. That rate increases, so you need more oxygen to the muscle cells. Right? There's a receptor that says, within the muscle saying, I'm running out of oxygen. So it's a receptor to receive the message of low oxygen levels in the muscles. Sends message to the central nervous system, right? Remember stimulus response model. Stimulus, receptors activated, sends the message to the CNS. CNS relays the message through the motor neuron to the effector. Remember, the effector is the gland, the muscle, or the organ to respond in some way. So, receives the message, low oxygen levels, send more oxygen. How do we do that? Increase breathing rate to get more oxygen in. Increase heart rate to pump a greater volume of oxygen, volume of blood containing oxygen to the muscles. The effect, oxygen levels increase. As you stop the exercise, message received, I'm not using up as much oxygen, I'm satisfied, sends message to the brain, through motor neuron to the heart slows down, breathing rate slows down as well. Yeah? Returning to that state of balance, returning to homeostasis. We don't talk about, later on in the year, we're going to talk a bit about the immune system. What happens when you have a pathogen, whether that's an infection or a virus, is that's disrupting homeostasis. And that's why you have a fever. That's why you have chills. That's why you cough. That's why you have an infection, because your body's fighting that. A pathogen in the body, something that is foreign to the body, right, is disrupting that state of control. Homeostasis is what we call negative feedback loops. Negative in the sense it's the opposing process to the stimulus. Yeah? So if oxygen levels go down, your body is responding to increase the oxygen levels to bring it back to a state of balance. Oxygen levels increase, your body slows down in order to bring back to balance. So let's think about the example of thermoregulation. Thermoregulation, right? We've got thermoreceptors on the skin. It's cold outside. Sends message, right? So the receptor is activated, thermoreceptor. Stimulus, it's cold. Thermoreceptor activates. Sends message to the CNS. CNS relays the message, motor neuron, to different responses. What are some of our responses when it's cold? Shiver. Why? What's that doing? That's muscle. That's a response with the muscle. Yes.
Like your muscles are retracting to get more blood into you.
Right. Friction. Rubbing together. Muscle cells are contracting. They're rubbing together. What does friction do? It generates heat. Right. What else is happening? Your hairs stand on end. What's the purpose of that? It's called piloerection. What's the purpose of that? Trap heat. Yeah. Hair traps a layer of air. Air is a good, relatively good insulator. So hairs on its end is trapping that layer of heat. It's also reducing the surface area of your skin. By slightly reducing the surface area of your skin, you're minimizing the heat loss to the environment. Yeah? So shivering, hairs standing on end, insulating the body, trying to bring that core temperature back up. So negative feedback. Stimulus is cold, body processes the information to do the opposite, wanting to bring back up the temperature. Let's think about the reverse. Right, step outside, sunny day, it's hot. What? Right, stimulus. It's hot. Thermoreceptors in the skin activated, sends a message to the CNS. CNS relays the message through motor neurons. What's the response? Sweat, right. Sweat is a gland, isn't it? Remember, muscle gland or organ are effectors. That's what elicits a response. So sweat is a gland. What does sweat do? Right. Pores open up on the skin. Liquid is allowed to go to the surface of your skin. Water has a really high specific heat capacity. It means it can absorb a lot of heat without changing temperature. So the water on the surface of the skin evaporates. As it evaporates, it's drawing heat away from the body. Body cools down. What else is happening? What else happens? There's more processes than just sweat when you get hot. Right? When you're cold, hair stands on its end. When you're warm, what happens to the head? Flattens. Flattens. Increases surface area. Yeah? Allows for greater distribution of heat. What else happens? Often you might go a bit flushed in the face or flushed skin. Yeah? What's that doing? Right. How? We call it vasodilation. What does vaso mean? Any thoughts? Vaso means vessel. Things like arteries, capillaries, veins. Vasodilation. What does dilation mean? Opening. Yeah. Vasodilation is the opening, the dilation of blood vessels, allowing blood to reach the surface of your skin, which is why you go flushed when you're hot, because blood is going to the surface of the skin. That allows for heat to get to the surface, to be distributed, and to escape. Brings your body temperature back down to that narrow limit. So negative feedback, negative, it's the opposing. The response is the opposing to the stimulus. We don't really look at positive feedback loops, but some examples of positive feedback loops are allergic reaction. So positive feedback loops are when the response is reactivating the stimulus. You get hives are itchy, you scratch them, or get bitten by a mosquito, you scratch it. You keep scratching it because, right, you're not removing the stimulus. You're activating the stimulus constantly, and the itch doesn't go away. So don't go scratching mosquito bites. Yeah? So allergic reaction, same thing. Your body produces histamine. It's a hormone that causes swelling. If you've got a particularly bad allergic reaction, you get boils, hives, big things, right? Swelling. Anaphylaxis is a response that affects major organs, the swelling throat, lips, affecting breathing, cardiovascular system, your core body system. What's the treatment for allergic reactions? Adrenaline? No, adrenaline is a stress hormone that allows for survival. That's not actually the treatment for allergic reactions. Who's heard of Telfast? Clarentine? What are these? What do we call them? Antihistamine. Yeah? Histamine's the protein. It's the hormone that causes the swelling. Anti means against or not. So antihistamine kicks in a negative feedback loop to reduce the swelling, reduce the allergic response. Other positive feedback is things like when a pregnant woman is in labor, it's activating the response of feel-good hormones, oxytocin, etc., in order to reduce the pain a woman is experiencing in labor. It's really important that we have homeostasis, that we have evolved in such a way it's for our survival, maintaining our body in these narrow limits, controlling body temperature, water levels. It's the reason you go to the toilet. Yeah? You can actually trick your body. Too much water, and that constitutes about 8% of your body weight, is too much water within a 24-hour period. So if I consume 8 litres of water, you are changing the electrolyte balance within your body. Now, it's different if it's a 40-degree day and you are an elite athlete. You need to be consuming about 1 litre an hour because that's how much liquid your body's actually getting rid of. On a standard day, 8% of your body weight. We can trick our body's electrolyte balances by drinking electrolytes. That tricks the body into thinking the electrolyte concentration is actually higher within the body, and you actually pee less. If you drink just water, you pee more. Something to think about. Okay, so we've talked about thermoregulation. We've talked a little bit about water balance. And we're going to talk about blood glucose levels. Talked about temperature, water. Okay. Blood glucose levels. What I want you to do is draw I'll show you this diagram. I'll go back. Blood glucose levels are controlled by hormones. Remember, the effector is a muscle, a gland, or an organ. Blood glucose levels are controlled through an organ response that delivers hormones. We've spoken about hormones. Yeah? So, receptor, two possible feedback loops. Too much glucose in the blood or too little glucose in the blood. Two different responses. Receptor is activated. The stimulus. Blood glucose levels are too high, often occurring straight after eating. Straight after eating, your blood glucose levels increase. Receptor receives the message, activated chemoreceptor. We're talking about sugar. Sugar is a chemical. Chemoreceptor receives that message. Sends the message to the CNS. CNS responds, motor neuron 2, the effector. The effector is the organ. The organ is the pancreas. Hello, pancreas. The central nervous system here. I'd like you to try and reduce blood glucose level. What does the pancreas do? Pancreas goes, okay, thanks for the message. I'm going to relay that message. I'm going to produce a hormone or release a hormone. Hormone it releases is insulin. Insulin enters into the bloodstream. Then the hormones are received by target cells. Target cells are the muscles and the liver. Sends the message to the liver, I want you to take up some of the glucose and store it for later. Glucose converted into a long carbohydrate called glycogen. Reduces the blood glucose levels. Negative feedback loop reduces the blood glucose levels. Blood glucose levels go down back to the state of normal. Other response. Stimulus. Hello. Pancreas, the blood glucose levels are too low. Pancreas goes, thanks CNS or thanks receptor. Got the message. Need to respond. Its response is to release another hormone. That hormone is called glucagon. Glucagon sends message to the liver. Liver, remember that glycogen you stored earlier? I need you to break it apart. Glycogen breaks it apart back into glucose. Blood sugar levels increase, brings back to homeostasis. Hypoglycemia, oh, we didn't talk about that. Diabetes, right, is an inability or an ineffective ability to produce insulin. Yeah? So it's a problem. We've got type 1 that is hereditary, right? That's a problem from birth. You've got an issue with your pancreas. Type 2 is often linked with diet. Metabolism it's just that ineffectiveness in producing insulin. So we need to, if you are diabetic, you need to take insulin. Typically 30 minutes after eating, you take insulin in order to reduce your blood glucose level. Hypoglycemic is too low blood glucose level. Hyper is too much. Same thing with hyper and hypothermia. Hyper is too much, hypo is too little. Glucagon, glycogen, pancreas. Yeah? So hypoglycemia too high can result in things like hypoglycemic. Someone will appear lethargic, really down, quite depressed, may go into a state of shock, may pass out. Hyper, fidgeting, irritable, may go, if it's really high, may go into a fit. Diabetes, we've talked about that, is that inability or ineffectiveness of insulin production. Insulin and glucagon are those two hormones. Insulin is the response to too high blood glucose levels. Glucagon is the reverse. Pancreas is the effector, that's the organ, and glycogen is what forms to uptake glucose into the liver or what breaks apart to bring that glucose into the body. Questions?